Hello students, welcome to session 2 on canals. Today's our session 2 includes the following contents. First one, definition of some important terms. Number 2, unlined and lined canals. And 3, design of canals by Kennedy's Hale. So now let us take one by one. Let us understand the definition of some important terms. The first term definition is gross command area, which is shortly called as GCA. This gross command area is nothing but it is the whole area enclosed within an imaginary line, which can be included in an irrigation project for supplying water to the agricultural fields by taking a network of canals. Second term is culturable command area, and shortly this is known as CCA. This is nothing but it is the total area within an irrigation project where the cultivation can be done and the crops can be grown. The gross command area GCA basically consists two areas. One is called culturable or cultural area. Other is called unculturable or uncultural area. So the area where crops can be grown satisfactorily, that area is termed as culturable area. And the area where crops cannot be grown satisfactorily, that area is called as unculturable area. Now let us move to third term, which is known as intensity of irrigation, and this is shortly called II. This is nothing but it is the ratio between the cultivated land for a particular crop to total cultural command area. Practically, having uh, some amount of land in some time duration due to some reason, the total area of land is not used to grow the crops. So intensity of irrigation is nothing but it is the ratio between the area of land used for growing particular crop to total cultural command area. Say for example, a farmer has a 5 acres of land and he uses only 3 acres of land for growing any crop type, then intensity of irrigation is nothing but it is the area of land used, that is 3 acres divided by total cultural command area, that is 5 acres. And this is generally expressed in terms of percentage. So for considered example, that is 3 divided by 5 into 100 will give us the 60% will be the intensity of irrigation. Moving to next term, that is the time factor. Again, this is the ratio between the number of days the canal has actually been kept open to the number of days the canal was designed to remain open during the phase period. So again, when a canal is uh, designed to construct, basically it is designed to keep open for some days to supply water to agricultural field during the phase period. But practically, it is not kept open for the designed period. So this time factor is nothing but it is the ratio between the number of days the canal has actually been kept open to the number of days the canal was designed to remain open during the phase period. Last term we are having is crop factor or crop ratio. We have the two seasons. One is Rabi season, other is the Kharif season. So this crop ratio is nothing but it is the ratio between area of land irrigated in Rabi season to that area of land irrigated in Kharif season. So these are the some definitions of important terms. Now let us move to next part, that is unlined and lined canals. Regarding these two types of canals, we already had gone through in session 1 in case of canal types. So let us take again unlined and lined canals here. Unlined canal is nothing but it is a canal which is constructed without the impervious thick layer on the channel bed and the sides or banks. So therefore, in unlined canals, seepage loss can be expected more. And these canals are generally constructed to the natural side. So therefore, these are designed with the low velocity to protect the canal section from scouring. Moving to lined canal are nothing but these are the canals provided with the thick impervious layer at the channel bed and banks. So in this canal type, seepage loss will reduce to some extent due to provision of impervious layer. And such canals are designed with the higher velocity rate, giving reduction in the cross-sectional area, as the lining is provided at the bank and bed of the channel. Now let us move to design part. So let us take design of canals by Kennedy's theory. Kennedy basically selected canal section in the region called Upper Barry Dove, and his selected site was supposed to be flowing with the non-silting and non-scoring velocity. And his study reveals that whenever the flow of water takes place through the channel section, the bed of the canal offers frictional resistance to the flow of water. And this is because of the generation of eddies. The eddies are generated due to frictional resistance between the flowing water and channel bed. So eddy generation takes place both in vertical direction as well as from the horizontal direction from the channel sides. But the eddies which are generated in the vertical direction, they are the most responsible to keep the silt in suspension. Therefore, the sediment supporting capacity is proportional to the bed width of the channel. Though the eddy is generated from the horizontal direction. They are not supposed to responsible to keep silt in suspension. So after his study, he given a relation as V naught is equal to Cm d to the power n. So practically we know that whenever a canal is designed with the higher velocity, the scouring can be expected more from channel bed and the size, which results in change in the shape of the channel. And when canals are designed with the lower velocity, then the silting can be expected more, which reduces the canal capacity. So he is given a relationship for velocity called critical velocity, that is nothing but V naught, and is given V naught is equal to Cm d to the power n, and the values of C and n most of the time remains equal to 0.55 and 0.64. So when values are not given for C and n, generally they are considered as C is equal to 0.55 and n is equal to 0.64. Finally, the equation for critical velocity remains equal to, after considering C equal to 0.55 and n is equal to 0.64, V naught is equal to 0.55 m into d to the power 0.64, where small m represents the critical velocity ratio, which is given by m is equal to v divided by v naught. So v is here represents the mean velocity of flow, and v naught represents the critical velocity. Kennedy used Cutter's equation to calculate the mean velocity of flow, that is v is equal to c root rs, where c remains a constant term, which again equal to 23 plus 1 by n plus 0.0015 divided by s whole divided by 1 plus under bracket 23 plus 0.0015 divided by s into n divided by root r. So the equation v is equal to c root rs. C is a constant term. R represents the hydraulic radius, and S stands for bed slope of the channel. And from constant C term expression, N represents the, or N is called as roughness coefficient or rugosity coefficient. S stands for bed slope of the channel, and R is the hydraulic radius. Now, knowing different quantities uh, such as rate of flow, roughness coefficient, n value, if it is assigned, the same value is considered for canal design. If not, the value of n is most of the time assumed as equal to 0.0225. Critical velocity ratio m is equal to mean velocity divided by critical velocity, and the bed slope s or d by d ratio. So knowing all these quantities, a canal design is done, uh, determining the hydraulic mean radius, mean velocity of flow, as well um, determining the channel dimensions. So now let us take case one type canal design, which includes the value of bed slope. So case one type problem, when bed slope S is given along with the discharge Q value. So when the value of discharge Q and S bed slope is given, uh, the following steps are uh, followed to design the channel. So in the very beginning step, that is in first step, the trial value of depth of flow is assumed for case one problems when discharge U and bed slope S is given. So in the first step, assume trial value of D, that is depth of flow. In second step, calculate critical velocity V naught is equal to 0.55 m into d to the power 0.64. So assuming depth of flow d value and substituting the same in critical velocity equation, in step 2, calculate V naught, that is critical velocity value. Then in step 3, calculate area A from discharge formula Q is equal to A into V naught. Step 4, knowing depth of flow and area of flow, calculate the bed width capital B. Step 5 consists knowing bed width B and depth of flow, calculate the wetted perimeter P. In sixth step, knowing area of flow and perimeter, calculate hydraulic mean radius R. So where R stands equal to A by P. In seventh step, calculate mean velocity of flow from the equation V is equal to C root RS. In step 8, if the critical velocity ratio is equal to 1, that is if M remains equal to 1, then assumed value of D is correct. That is in step 2, we are calculating the critical velocity value, and in step 7, we need to calculate mean velocity value. Knowing both velocity values, it is required to calculate the critical velocity ratio, that is M value, where M is equal to mean velocity divided by critical velocity. If in step number 8, the critical velocity ratio results equal to 1, then the assumed trial value of T remains correct. If not, that is, if critical velocity ratio M value results other than 1, then that represents the assumed trial value of D is incorrect. Therefore, in step 9, we have to go for revise the depth of flow D value. Means we have to assume other depth of flow value and we have to follow the same steps to design the channel. Now, to understand in detail, let us consider an example here. So in this problem, the definition stands for design and sketch an irrigation channel to carry 5 cubic. The channel is to be laid on a slope of 0.2 meter per kilometer assume n is equal to 0.025. It should be 0.0225 and m is equal to 1. Now we have to implement the design steps here. So in the problem definition, we have the discharge Q value equal to 5 units and bed slope S value is equal to 0.2 meter per kilometer. Along with these, we have the roughness coefficient value n is equal to 0.0225 and m is equal to 1. So now in the first step, but assume the trial value of depth of flow. So let us assume depth of flow d is equal to 1 meter. Now from the Kennedy's equation, that is V naught critical velocity V naught is equal to 0.55 m into d to the power of 0.64. Substituting the values of m and d, so V naught results equal to 0.55. In third step, from the discharge formula Q is equal to area into velocity, area results equal to Q divided by V, that is discharge Q is given 5, velocity is 0.55, critical velocity, so that equal to 9.09 meters square. So in third step, area results equal to 9.09 meters square. In step number 4, from the area formula, the value of B is obtained here, considering A equal to 9.09 meters square and depth of flow D value equal to 1 meter. B is obtained here equal to 8.59 meter. In step 5, perimeter value is determined and it is substituting B value and D value. It is resulted equal to 10.83 meter. Step 6, hydraulic radius R is equal to A by P. Substituting area value and the perimeter value are resulted equal to 0.84 meter. And in 7th step, from Putter's equation, the mean velocity of flow is equal to C root RS. So before we calculate mean velocity, we need to calculate the value of C. So here in the C term, we are having reversibility coefficient n and the bed slope S. So substituting n value and S value, C resulted equal to 42.85. And finally, V resulted equal to, after substituting R value, S value and C value, equal to 0.555 meter per second. Now taking the ratio of velocities, m resulted equal to 1. Hence, the assumed trial value of T is correct. If it results incorrect, then we need to go for revise the design steps. So, this is what we are having in today's session. So, remaining part of the canal design will take in next session. Thank you.